6 little blobs planned a secret Santa and were exchanging gifts with each other. Each blob prepared a gift with their own color. One of the blobs asked, "How many ways can we exchange gifts so that no one gets their own gift?" You may think of using 6 factorial, but that way some blobs might get their own gifts. For the gift exchange, each blob must pass the gift to another blob. We will use arrows to denote how the gifts are being exchanged. This means each blob gives one gift and receives one gift. The crux of this is that no gift goes back to its own blob, which we call the derangement of n, or in short, dn. First, let's solve an easier problem, finding the number of derangements where red passes the gift to blue. Looking at the arrows, we can think of all the blobs being connected in loops. Since we only want to find the number of derangements where red passes the gift to blue, we will only consider the loop size of the blobs connected together in the loop with red and blue. So the minimum loop size is 2, which is when red and blue pass the gifts to each other. For the rest of the gifts, we can think of this as a smaller version of the original problem. Remember, dn denotes the number of ways that n gifts can be permuted such that they don't return to their original owners. Hence, the number of ways to derange the rest of the gifts is d4. For a loop size of 3, meaning one other blob is connected in the loop with red and blue, there are 4p1 ways to choose this blob. Then there are d3 ways to derange the other gifts. For a loop size of 4, meaning 2 other blobs are connected in the loop with red and blue, there are 4p2 ways to choose and order these 2 blobs. Then there are d2 ways to derange the other gifts. You can already see the pattern start to form. For a loop size of 5, there are 4p3 ways to choose and order the 3 blobs, but the last blob will always receive its own gift, so there are 0 possible derangements, denoted by d1. For a loop size of 6, there are 4p4 ways to permute the 4 blobs. Putting these together, we get this.
Let's look at all possible conditions, not just red to blue. For every possible derangement, exactly one of these 5 conditions must be true. This is because each blob, including red, must pass the gift on to another blob. And since red can only pass out one gift, these 5 conditions are mutually exclusive, so we can just multiply by 5 to find the total derangements. We can generalize the formula by applying the same logic to any n derangements. To find an exact formula, we just have to solve some recurrence relations. Firstly, we substitute in the permutation formula and write the entire thing in sigma notation. We can then take out the first term of the summation and rewrite the expression. And you can see, if we replace n with n-1 in the initial formula, it looks the same as what we have down here. After substituting, we get a nicer 2-term recurrence relation. Let's subtract n times dn-1 on both sides. After simplifying, we see that if we replace n with n-1, this is the same as what we have up there. We can substitute all the way until we get d2, which equals to 1, and d1, which equals to 0, and then get an even nicer 1-term recurrence relation. Let's divide both sides by n factorial. Once again, if we replace n with n-1, this is the same as what we have up there. So we can substitute a few times until we get to d0, which by definition is 1. And then we can rewrite it in sigma notation to get the exact formula. One more thing, if you are familiar with the Maclaurin series, by substituting x equals to -1 into the Maclaurin series of the exponential function, you will find something really cool. dn and n factorial only differ by about a factor of e. Or you can say the limit as n approaches infinity of n factorial over dn is e. So back to the question, by substituting 6 into the formula, we know now that there are 265 ways that the blobs can exchange gifts. And now the little blobs are happy.